Hash functions are, as the name indicates, functions mapping elements of a certain input domain to elements of a certain image domain. In the example listed, the hash function h, for example, maps the element x1 to the element h of x1 and maps x2 to the element h of x2. Additionally to just being a function, a hash function is a function that is easy to compute and a function whose input domain is binary strings of arbitrary length and whose image domain is binary strings of a fixed length. Instead of just the four elements x1 to x4 listed, the input domain for the hash function h would thus contain many more elements and would actually be of an unbounded size. The image domain may very well just contain the three elements listed, however, as the image domain of a hash function is of a fixed and bounded size. From the core structure of hash functions, which map binary strings of arbitrary length to binary strings of fixed length, meaning that the input domain of a hash function is much larger than the image domain of hash values, the essential observation arises that for any hash function, there are always different elements in the input domain, for example the x1 and the x4, that map to the same hash value, and such a pair, like the x1 and the x4, are then said to be a colliding pair of inputs. This is necessarily the case for all hash functions, meaning that all hash functions have collisions. For a hash function to be useful for cryptography as a tool to allow the verification of the correctness and completeness of information, a hash function would actually need to be injective and uniquely map inputs to hash values such that no two different inputs would have the same hash value. Phrased the other way around, injectivity would allow us to conclude that if two objects have the same hash value, then these two objects would actually be the same object. This, however, is impossible, as we have just seen on the previous slide, where we have observed that all the hash functions have colliding pairs of inputs. Injectivity, we now know, is an impossible property of hash functions, but exactly the property we will need hash functions to have in order to serve cryptographic integrity-related purposes. Given the impossibility of injectivity, this property is approximated by demanding the property of collision resistance. Contrary to injectivity, which asks for hash functions to map inputs uniquely to hash values, collision resistant now demands that it must be merely difficult to find different inputs that would be mapped to the same hash value. The pair of x1 and x4 in our example would thus be difficult to find if our hash function h would be a collision-resistant hash function. Related to the property of collision resistance is the property of second pre-image resistance. Second pre-image resistance is the property demanding that given for a very specific input, let's say the x4, it must be difficult to find a different input that maps to the same value as the given specific input. In our example, if x4 is the specific input we are provided with, it must be difficult to find x1, which forms a colliding pair with x4. It's now interesting to observe that if a hash function is collision resistant, meaning that the game of finding colliding inputs to the hash functions can't be won, then the game of finding for a very specific given input a different input that would collide with the given input can't be won either, thus meaning that a collision resistant hash function is also a second pre-image resistant hash function. Phrasing this the other way around, a hash function that's not second pre-image resistant is a hash function that's also not collision resistant. Quintessential to a hash function being collision resistant is that the hash function needs to be a one-way function. A one-way function is a function that is easy to calculate in one direction, but not in the other direction. In our example, one-wayness would mean that it is easy to calculate the hash value of, for example, x1, but it's difficult to calculate the input x1 if we are just given the corresponding hash value h of x1. The reason one-wayness is essential for hash functions is due to the fact that hash functions not just have a few colliding pairs, but that generally speaking, hash functions have an unbounded number of collisions on every single hash value. To understand why, assume we start with an input domain that's the same size as the domain of hash values. In that case, we can actually have an injective hash function, but as soon as we add just one bit more to the size of the input domain, we double the size of the input domain, and with this, even for a perfectly well-balanced hash function, would have at least 2 collisions on every single hash value. If the size of the input domain is larger by 2 bits, the size of the input domain is 4 times the size of the domain of a hash value, and every hash value would have at least 4 collisions on it. Hash functions now have an unbounded input domain, and with this, it's clear that for each hash function, there is an unbounded number of collisions on each and every hash value. If the hash function now would not be one-way, meaning we could, given a certain hash value, calculate an input that would be mapped to this hash value, then due to the unbounded number of collisions on the hash value, we would very likely calculate a different input from the original input, but an input that nevertheless maps to the same hash value, which all in all means that if our hash function is not one way, we, with a very large likelihood, also don't have collision resistance. Summarizing our previous observations about hash functions, we get to see that hash functions are only useful for cryptographic purposes if the hash functions are one-way and collision resistant. Such a hash function with these two properties is then referred to as a cryptographic hash function and can be used as a primitive to realize the classic cryptographic security goal of integrity. It's now time to look at examples of real-world hash functions where we find that the hash functions used by real-world systems are often either the message digest 5 MD5 hash function or then one of the secure hash algorithm hash function family SHA-1, SHA-2 or SHA-3. Message digest 5 MD5 is a hash function released in 1992 and developed by Ronald Rivest, who is none other than the R in RSA and co-created RSA in 1977. MD5 produces hash values of length 128 bits, and indeed, if we use, for example, one of the many online services calculating MD5 hashes and feed it the input string fundamental cryptographic hash functions, we will get a 128-bit string as a result, which in this specific case will read, if translated into a hex string, 6, D, 7A, and so forth. SHA-1, the secure hash algorithm 1, was then developed by the US National Security Agency NSA and released in 1995. SHA-1 produces hash values of length 160 bits, and the 160-bit SHA-1 hash value for again the same input fundamental cryptographic hash functions, then reads 5E, FFE, and so forth when translated into a hex string. SHA-2, the secure hash algorithm 2, was again developed by NSA and released in 2001 and can produce hash values of either 224 bits, 256 bits, 384 bits, or 512 bits. The SHA-2 256-bit hash value for again the same input fundamentals of cryptographic hash functions would then produce a 256-bit hash value that reads 41, BFA, and so forth when translated into a hex string. SHA-3 The newest addition to the SHA family was the result of a 6-year global competition for a new hash standard and was released as a new NIST standard in 2016. Similar to SHA-2, SHA-3 can also either produce 224 bits, 256-bit, 384-bit, or 512-bit hash values, and if we calculate the 512-bit SHA-3 hash value for, again, the same input fundamentals of cryptographic hash functions, we get the 512-bit hash value for 8 CED when translated into a hex string. These are the workings of 4 of the most prominent hash functions currently out there. I presented these hash functions in a matter-of-fact attitude. What is left to discuss now is whether all of these 4 hash functions are secure hash functions recommended to really be used for cryptographic purposes.